Mass and energy balance for biosystem. Module 6. Conservation of mass. Segment 1. System with multi-component mixture. Ismi Lily from School of Life Sciences and Technology, Institute Teknologi Bandung. In this module, we will discuss about the system with multi-component mixtures, system with multiple units, and system with chemical reaction and dynamic system. And in this segment, we will focus on the discussion about the system with multi-component mixtures. In the system with multi-component mixture, consider system with mass entering and leaving in streams. Each chemical species or compound S in each stream is associated with its special flow rate, such as mole of S per time or mass of S per time, and the total flow rate of the stream in either moles or mass can be calculated by summing the individual species flow over all species S that present in the stream. And for the equation can be seen in this slide. An alternative way of representing a stream is to give its total flow in rate of either moles or mass together with the composition of the stream. And two convenient measures of composition of a species are the mass or weight fraction and the mole fraction. All mass and mole fraction of all species in a stream must sum to 1, as shown in the equation below. Mass and molar flow rates for a particular compound S are related to one another through the molecular weight as follows. And for the mole flow rate can be calculated as mass flow rate is divided by the molecular weight. Mass and mole fraction are related to mass and molar flow rate, respectively. The equation can be seen in the equation below. And for the interconversion between the mass and molar units can be obtained as equation below. The derived equation can also be formulated for a chemical element in a system, and the equation would contain P subscript in place of the S subscript. The differential conservation equation from previous segment for system containing multiple inlets and outlets can be extended to systems that contain multiple species in each stream. And for open, non-reacting, and steady-state system, the following mass conservation equations are written for the species mass, and for the element mass, for the species moles, and for the element moles. In some systems containing multiple components within their boundaries, an individual component can come from a single inlet source, mixed together with components from other inlet streams, and exit through a single outlet. For example, consider a simplified model of the stomach, where one of the primary functions is mixing. Neglecting any chemical reaction facilitated by gastric juice, no digestion or breakdown of food, the stomach can be modeled as a non-reacting system. As shown in the figure, the stomach has two inlets, the esophagus and the gastric glands, and the stomach has one outlet, that is the duodenum. All individual components enter by either the esophagus or the gastric glands. It cannot both mix together in stomach and exit the duodenum as chyme, a multi-component mixture of all the substance. When one inlet is the only source of a specific component in a multi-component mixture, and the mixture leaves through only one outlet, we can use equation below to find the mass flow rates into and out the system. And since species S is contained in just one inlet and one outlet stream, so the mass flow rate can be written as in the equation here. To illustrate the process of setting up steady-state conservation equation for particular compounds and for the overall system in a multi-component stream system, consider a mixing tank. And in this figure, the stream 1 contains compound A and B and has a total mass flow of m.1. And the mass fraction is W1A and W1B. And for the stream 2, it contains compound B and C and has a total mass flow of m.2, and the mass fraction is W2B and W2C. And for the stream 3, it contains compound A, B, and C and has a total mass flow of m.3, and the mass fraction is W3A, W3B, and W3C. And for each compound in this non-reacting steady-state system, a species mass conservation equation can be written as the summation of the mass fraction input of compound S multiplied by the mass flow rate of input minus summation of the mass fraction of output of compound S multiplied by mass flow rate of output is equal to 0. Thus, an equation can be written for each of the compound A, B, and C using equation below. And the total mass balance on the system is mass flow rate 1 plus mass flow rate 2 plus mass flow rate 3 is equal to 0. And for the next segment, we will discuss about the system with multiple units. Until then, I'm Lily from Institut Teknologi Bandung.